بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so let's continue to talk about linear algebra and NumPy and their practical applications and foundations in data science. Today we are going to talk about some new concepts or some additional concepts like the determinant of a matrix, the rank, the full rank matrix, the inverse matrix, the pseudo-inverse matrix, and how to solve a linear system. Okay, so the determinant of matrices is an important aspect, and it's scalar value that you can calculate out of the matrix, and it's calculated using the Laplace expansion or using elementary row operation. So let's look at the case of small dimensional matrix like 2 by 2 or 3 by 3. Imagine that you have a matrix A, B, C, D like this. So the determinant of a matrix is A multiplied by D, these diagonal values, and C minus C multiplied by B, these diagonal values. In the case of 3 by 3 matrix, okay, having values from A to I, so this is the equation. But of course in NumPy, we have already some tools that allows to calculate the determinant of a matrix. And one of the important features or characteristic of the determinants is that it can tell us whether a matrix is invertible or not invertible. If we can inverse the matrix. Not every matrix you can calculate its inverse. So if the determinant is 0, you cannot inverse this matrix. Okay? If the determinant is different from 0, in this case, you can inverse the matrix. This is one of the usages of the determinant, is to know whether you can, for example, if you want to solve something like we will see later on, the linear equation ax plus b. So if the matrix is invertible, we can calculate a minus 1 and then multiply it by the two sides, and we can find a solution to that system. But if the matrix is not invertible, so there are other ways on how we can solve linear equations. Okay, this is an example, a numerical computation with the matrix A with 4 numbers. So the determinant of the matrix A here, by applying this equation, we will find is equal to minus 2. And here the interpretation, since the determinant is different from 0, so matrix A is invertible. We can calculate the inverse of the matrix. Okay. So in NumPy, you can easily calculate the determinant of a matrix by using np.linearalgebra subpackage.det, and you put the matrix as an argument, and finally you can get the argument of that matrix. So this is the first concept. The second concept is the rank of a matrix. So the rank of the matrix is basically defined as the maximum number of columns or rows that are not dependent linearly independent. So what does this mean? Let's look at this example. This is a matrix. It's forbidden to drink and eat during the lecture. Okay, for everyone. So let's look at this matrix. What do you observe? Look at this row, and this row. What do you observe?
This one is a multiplication of this one.
Yeah, so we can say that this row, if we multiply 2 by 4, we'll find 8, 4 by 4, 16, and 1 by 2. Okay, so yeah, this is not linearly dependent. Okay, maybe the rows? The columns, yes. So if you multiply 2 by 4, 2 by 2 is 4, 8 by 2 is 16, 0 by 2 is 0. So here we have an example of these two columns are linearly dependent. They depend with a linear transformation. So here, although I have a matrix of 3 by 3, so the dimension of the matrix is 3 by 3. But the rank of the matrix is only 2. Okay? Because these two columns are linearly dependent. Okay, and this is the definition here. It corresponds to the maximum number of linearly independent columns or rows. And this is the formula, is the dimension of column A or row A. Okay. Yeah.
If we have two columns that are the same, we say that they are linearly dependent.
Yeah, linearly dependent, the factor is 1.
Yes. So do we say that the whole matrix is linearly dependent, or just
No, we say that the matrix doesn't have a full rank. So it has a rank minimum, okay? We will talk about the full rank right now. And the importance of the rank is because it allows us to know whether the linear equation system okay, we will have now in this lecture how to solve this linear equation system, whether there is a solution or not. Okay, so if A is a full rank, is a full column rank, so the system will have a unique solution with B in the column space of A. So this is one of the important characteristics why we look at the rank. So if it is not full rank, in this case we might have either no solutions or multiple solutions. But if it is full rank, we will have a unique solution to this linear equation system. Okay, and this is an example here. You can calculate the rank using np.linearalgebra.matrix rank A. So this is going to give 2, obviously, because we have 2 columns that are linearly dependent.
So,
Yes.
The matrix is 2 by 2 and rank is 2. Do we call it a full rank?
Yes. If it is equal to the maximum of the number of rows and columns, it's a full rank. Yes. So now calculating the inverse of a matrix. Okay, when the determinant is different from 0. Okay, if A is non-singular, it means determinant is different from 0. Then the inverse of the matrix exists. So we call singular matrix is a matrix that the determinant is 0. It's not invertible. And the characteristic of the inverse of the matrix is that when you multiply a matrix by its inverse, it's going to give the identity matrix. It's like you take a number, a scalar, and you multiply this number by its inverse. 5 multiplied by 1 divided by 5 is equal to 1, the identity, scalar identity. Now the same thing here. If the matrix, the determinant of the matrix is different from 0, there is a way to find the inverse of that matrix. And this is a numerical example here. We have A equal to this, 1, 2, 3, 4, and B, 5 and 11. So we can calculate the inverse of the matrix and solve the equation. So in this case, x equal to minus 1.5 and 3.5. So this is how we apply this in Python. So we can calculate, if you want to solve this linear equation system, we can calculate the inverse of the matrix using dot inv A. And finally, we can make the dot product of A inv and B, and then we will find the value of x. So we can calculate the inverse of the matrix when the matrix is a square, okay, and have non-zero determinant. But if the matrix is not square, okay, now there are 2 cases, there are several cases, whether the matrix can be a full rank or not a full rank. So a matrix A of dimension m multiplied by n, so we have m rows and n columns, is said to have a full rank if the rank of A is equal to the minimum of its number of rows m or n. Okay, so the minimum of n, if I have 3 by 4 matrix and the rank is equal to 3, in this case we say that we have a full rank because we don't have any linear dependency between the rows and the columns. Okay, so we can have a full row rank or a full column rank. So a full row rank is when m is smaller than m smaller than n, and the opposite, the full column rank, when we have n, the number of columns is smaller than the number of rows. And if you have a square matrix, in this case the rank will be equal to same thing, m is equal to m. And of course the determinant must be different from 0. So let's look at some examples. Now this example is a 2 by 2 matrix with a full rank. Why it is a full rank? There is no linear transformations between the rows and the columns. We have 2 by 2, so the rank of this matrix is 2, since both rows are linearly independent. Let's look at this one. This matrix is not a full rank, although it is a square matrix, but it's not a full rank. Because here, if I multiply by 2, either in the column wise or the row wise, we're going to find that there is a linear dependency. Okay, the second row is just 2 times the first row. Same thing, even the column is 2 times. This column is 2 times. This column is 2 times this one. So the matrix B here, although it is square, is not a full rank. Look at this case. Now this is a rectangular matrix. It's 3 by 2. So do we have linear dependency? We don't have. So what is the rank of this matrix? It's 2. We have 2 columns and 3 rows. So we take the minimum. We take the minimum. And here, since we don't have linear dependency between the rows and the columns, we have a full rank matrix. And this is a 3 by 3, and it's not a full rank matrix because we have a linear dependency. The third row can be written as a linear combination of the first two rows. Look now, it's not a multiplication, but this one can be a linear, this row can be a linear transformation of the first two. 3 plus 9, or 1 plus 2 is 3. 4, we don't have this one. This is not linearly dependent. Is there any dependency here? It's a linear combination of all the different numbers. It's not just element-wise operation. Okay, so now why we talk about full rank? So if the matrix is not squared, it's not inversible. So in this case, when we have a matrix that is a full rank, when we have a matrix that is not full rank, we cannot calculate its inverse. And the alternative here is what we call the pseudo-inverse matrix. So what is a pseudo-inverse matrix? It is denoted as A plus, and this is a generalization of the concept of the inverse, but applied to non-square or to the matrices that are not full rank. Because non-full rank and non-square matrices are not inversible. So what is the definition now? It's not the definition that A multiplied by A minus 1 equal to I, because we cannot calculate A minus 1. So the definition here, it satisfies the condition A multiplied by A plus multiplied by A is equal to A. So if we find a matrix, or if there exists a matrix that satisfies this condition, we call this matrix as the pseudo-inverse. And it has usages in several machine learning applications. It's called the pseudo-inverse matrix, and it satisfies this condition or this condition.
How do we get it?
Yeah, by applying solving linear equation system, you can get it, like we do for inverse when the matrix is inversible. There are algorithms that allows you to find this. Now, when you use this in Python, you just need to calculate to call the function p_amp. This is the pseudo-inverse of V, and the pseudo-inverse, it will satisfy this condition. And A plus exists for any matrix that is square or non-square. So the existence is always guaranteed. It applies for full rank, non-full rank, square, and non-square matrices. So the difference with the inverse matrix, okay, a regular inverse matrix only exists for square and non-singular matrices. Non-singular, it means the determinant must be different from 0. And the pseudo-inverse can be computed for any matrix. So there is always a matrix A plus that can satisfy this equation.
So why don't we just generalize the use of pseudo-inverse? Because it applies to all matrices.
No, but the inverse is stronger. Okay, when you want to solve a linear equation system and you have the inverse, you're going to have an exact solution. These will be kind of approximate solutions, not exact. Okay, any questions? Okay, so this is how we calculate, is using p_amp here. And this is an application. Look at this application. This is an example of a linear regression for sequence labeling using pseudo-inverse. So in machine learning, usually, we try to develop algorithms that try to identify entity names. For example, in this sentence, John works at OpenAI. We have an entity name, it's John. Okay? For example, Riyadh is also an entity name. So this is important because sometimes, imagine that we want to preserve the privacy of a text and we want to remove every name inside the text. So sometimes we need to identify names of persons, locations, and anything that we can call as named entity recognition. Okay? So, and here we can use the pseudo-inverse as an approximation to tell about the existence or predict whether a sentence contains a pseudo-entity name. So this is a very simple example just to illustrate the concept. We have here a collection of data set. We have the input, which is a text. Okay, for example, John works at OpenAI. It contains an entity, a named entity, which is John. So here it's 1. And here yesterday was very sunny. We don't have any entity name. So here it's 0. She bought 300 shares of Tesla. Tesla is an entity name. And here we don't have any entity name. So this is just an example. And this is the Python code that captures this example. Here we have snippets and labels. So the second phase is to extract the features. Now we have text. Text doesn't mean anything. Of course, there are many ways on how to extract the features using embedding. One of the solutions is TF-IDF. It's an algorithm that is able to extract feature names. So we have here several names. So we're going to extract 5, max feature equal to 5 here, and convert them so it will fit to create an embedding for each one. So we can use this matrix now, which is a feature matrix that contains the most important word that we want to look at. And now we can use the pseudo inverse, okay, the A plus. Since A is typically overdetermined, and we compute the pseudo inverse A plus to find the least square solution for the linear system. So finally, we can use an approximation of the inverse, okay, because here what do we have? We have A and we have B, and we want to find X. So if we consider that there is a linear relationship between this matrix and these labels, okay, and we want to have an approximate solution, we can, and this matrix is not inversible, it's a rectangular matrix. So one of the possible, it's not the best, by the way, okay, because there are machine learning techniques that can provide you, but one of the approximations that could work in some cases is to calculate the pseudo inverse and use the pseudo inverse as the inverse of the matrix to have an approximation of the solution. So this will be an approximate solution. Of course, if you have the inverse and you have a strong linear relationship, you will find one solution of that system. Does this make sense? Okay. And this is the whole code, just showing the application. It's a dot product between P inverse and the label, a NumPy array, that will find an approximate solution of the value of X. Okay, so now all of this is just an introduction to module number 6, which is the systems of linear equations. And this is one of the popular applications in linear algebra, in data science, and machine learning. So I think you have already went through this type of linear equation systems. You have a system of equations with n unknown, okay, and you have the coefficient, and you have the output, and you want to find what is the correct value of X, okay, given A and B. Of course, in the best case, when A is a square matrix and is inversible, the solution is simple. We will take the inverse of A, multiply by B, and you will find X, okay? But A is invertible is not always possible. So there are other ways that can also help to solve this type of linear equation system, and one of them is called the Gaussian elimination, and another one is the decomposition of the lower and upper triangle matrices. Okay, it's not a big deal. We're not going to go into details, but I'm presenting these different techniques, so at least you are aware of them. So in Python, we can use np.linearalgebra.solve to find the solution of the linear equation system Ax equal to B. So when you use .solve, this is going to apply the Gaussian elimination. Okay, this is how it works. So you have a matrix A and you have a matrix B, and you want to find the value of X, okay, such that Ax equal to B. So using .solve, you will find the solution of that linear equation system. So this is matrix A, matrix B, and this is the result of applying .solve. So how it works, the Gaussian elimination, it's a method for solving linear equation by transforming the system matrix to an upper, to an upper triangle form using row operations. Yeah, let's look at this example here. You have a linear equation system similar to this one. So basically, you have a matrix. You have a matrix of A11 to A33. And in order to solve this one, we will try to convert this matrix into a triangular matrix, an upper triangular matrix. So here, we will do a transformation of the coefficients. And it's basically, it's a substitution. Usually, we start by trying to isolate one of the variables, okay, and then isolate the second variable until we will have a value for one variable, and then we back propagate, okay, or back substitute in the opposite way. I think all of you have already done this, even in high school, okay, at small scale. Okay, so this is the Gaussian elimination. It's a known technique, and this is how it works. Just one iteration of this. We have a linear equation similar to this one. So, you know, technically speaking, we call it the row echelon form. We provide the coefficient of the matrix and the output over here. And then we will try to find a linear transformation between the rows and the columns. And this is going to result into zeroing some parts of the matrix. Okay, so it's like isolating one of the variables and zeroing some part of the matrix. So this is one iteration. After doing several iterations, we're going to have an upper triangular matrix that will allow us to back substitute and find the value of x3, for example, x2 and x1. So the LU decomposition, it splits the matrix into two factors, a lower triangular matrix and an upper triangular matrix U. So we can write A equal to L multiplied by U. Usually we can decompose any matrix to upper triangular and lower triangular multiplication of both. This is one of the characteristics of matrices in linear algebra. So if we do this decomposition, we're going to have A is equivalent to the multiplication of this matrix by this matrix. Okay, here we have a diagonal of ones. Here we have values in the lower part, and here we have U11 to U33, or an upper triangular matrix. And based on this, we can actually try to solve the linear equation system by, first of all, calculating the value of y. So if we find the L and the U, so this is the matrix A, we do an LU decomposition. So matrix A will be the sum or the product of L multiplied by U. Now we try to find the value of y, which is that satisfies the lower matrix multiplied by y equal to B. This is going to find the value of y, and then we will apply the equation Ux equal to y. And because they are triangular, they are much easy to find the solutions with triangular matrices, either upper or lower. You know, simple. By doing simple computations, we can find the results. And finally, we can use matrix inversion if the matrix is invertible, as you can observe. So this is an example. We already talked about it. So first of all, you need to calculate the determinant to see whether the matrix is invertible or not. If the determinant is different from 0, in this case, we can calculate the inverse of the matrix, apply it to B, and finally, we will find a solution to the linear equation system. Okay, so this is a Python example. We have a matrix A equal to the NumPy array 3, 2, 4, 1. We have the vector B. Now, before doing the inverse of the matrix, we calculate the determinant. Okay, it is different from 0. So in this case, we inverse. Okay, np.linearalgebra.inv of A. And finally, to solve the problem, we multiply the inverse of the matrix multiplied by B. Here I did a transpose. If you don't do the transpose, you will not find the same as the theoretical computation. Okay, so it's needed to do the transpose over here to find exactly the same computation in practice. Transpose, the rows becomes columns and the columns become the rows. Okay, so let's illustrate this graphically. What does it mean solving a linear equation system? Now imagine that you have this representation. This is the linear equation system that we want to have. So we can convert this into equations, parametric equations. So this is equivalent to finding 2x1 plus x2 equal to 5 and x1 plus 3x2 equal to 7. Let's say x and y. So we can represent this in a two-dimensional space. This is the equation of a line, and this is the equation of a line. So what will be the solution? The intersection point. Of course, if the two lines are parallel, you will not have a solution. Okay, so this could be equivalent to the determinant is not inversible. So there is no solution. Okay, so this is just to provide you some kind of illustration on how we can visualize this in practice in two-dimensional space. Now what if we have three-dimensional space or n-dimensional space? Okay, so a line basically, it's a two-dimensional plane. Okay, if we look at three-dimensional space, we're going to have planes which are like 2 dimensions, in 2 dimensions. Okay, so this equation is an equation of a plane in space. Okay, if you have had geometry courses, okay, this is the equation. This is the equation of a line, and this is the equation of a plane in 3-dimensional space. And if we go to n-dimensional space, we talk about hyperplanes. Of course, we cannot visualize them in 4th dimension or in 5th dimension. So what will be the solution of this? It will be the intersection. So we will not have one solution. We will have the intersection of these three planes, which is the first plane, the second plane, and the third plane. So let's finish today's lecture about a case study on how we can use AX equal to B in data science. Imagine that you would like to have a model that allows you to calculate, to estimate the price of a house based on its area. And you collected a data set and you have these different points. It's not a perfect line, but could be approximated with a line. This is what we call linear regression. It's a regression line that allows you to make a prediction of particular outcome based on a certain input. So it's not going to be a very bad solution if we approximate the relationship between the area and the price as kind of linear. And in this case, we can have recourse into solving a linear equation system where we have X is the area and Y, which is B, will be the price. Okay, and we want to find the vector X, which is a weight vector that can transform the values from the area to the price. Does it make sense? Yeah. Okay, so this is just to tell you that everything, we talked a lot of theory today, but this theory is being used in practice. And this is just a very simple example on how we can use this theory. And now let's assume that we have a matrix A that has features of the house. Okay, a feature, for example, we have the area, we have the bedrooms, and the age. Okay, so for this house with these features, the price is 400, let's say. For the second house, we have 250, and for the third house, we have 300. Let's assume that this is a data set, and we assume that we have a linear relationship between the features and the price. And now we want to find a weight vector that can do this transformation. Of course, this is only valid if the assumption of linear transformation is correct, which is not in practice. Okay, but this is just a simple example. Now, if we know that this assumption is correct, we can use the techniques that you have mentioned before. Okay, for example, here we can use to predict the house. So this is called the least square method. It's one of the possible ways. We can also use the inverse of the matrix or the pseudo inverse of the matrix, because this matrix, it's 3 by 3. It could be inversed if yeah. And using the least square method applied on A and B, we can find that here we have X minus 4.5 and 0.18 as the equation of this line. Okay, so the slope here is represent the equation of this line. This is another example where we apply linear algebra in spam detection. Okay, so imagine that you want to detect whether you have spam or not spam on an email based on the features or the frequency of the words like free, winners. When you receive spam, there are some common keywords. So early spam detection, they are based on the frequency of these kind of words in order to detect. Of course, now we use completely different techniques using word embedding and more advanced machine learning and deep learning techniques. But in the early days, they were using this type of very simple machine learning models to find a transformation, linear transformation between these features and also a binary classification. So if we want to have a model, we need to have an input. For example, look, we have emails, 1, 2, 3, 4, 5. And every email we will have a label, whether it is spam or not spam. For example, this one, free money now, click here. So this is spam, we're going to label it as 1. And the second one, hi Bob, what about the game of golf tomorrow? So this is not a spam. So this is the data set. We know the input and we know the output. Of course, we can use machine learning techniques like neural networks and so on, but now we can actually vectorize these keywords, okay, creating an embedding representation of these keywords or a vector representation of these keywords as already introduced. And then we can use the least square method or the inverse of the matrix in order to find the value of X that will allow the linear transformation. Of course, here we still assume that we have a linear transformation between the keywords and the labels. Yeah, so that's pretty much it for today.